So I want to show you an interesting problem that we can do with this. Here's the value of that big G. Remember, the equation that we're using is right here. The force due to gravity is big G m1 m2 over r squared. All right. I want to see if from all this information, here's big G. That's a constant that never ever changes. That's the same everywhere all over the universe. And here is the radius of the Earth. I want to see if we can use this information to calculate the mass of the Earth, maybe. So here's what I'm getting at. Let's say here's the Earth, and let's say here is some object sitting on the Earth. So we know, technically speaking, that the Earth, which I'm going to represent here on a free body diagram, is gravitationally attracted to that object, and that object is gravitationally attracted, I'm going to call this M, and that object is gravitationally attracted to the Earth. That's how gravity works, an attractive force between two masses. And these forces are equal. It's a third law pair. So I can calculate the force here, the force due to gravity, with this equation. But wait a second. Don't I have another equation that can help me find the force due to gravity of an object near the Earth's surface? I do. I could say that the force of gravity felt by object M dealt by the Earth is going to equal, do you guys remember? M times little g, the mass of this object times little g. So here's what I can do. I can say that, okay, if this is the force due to gravity on this object, and now I have another equation that also represents the force due to gravity on that object sitting on the Earth's surface, can I not set them equal to each other? I can. So I can say that I'm going to call this M1 G, this is the mass of object 1, is equal to big G, the mass of object 1 times the mass of object 2. Well, what's our second object in our system? The Earth, right? The mass of the Earth over r squared. Do you guys see how I could use this to actually calculate the mass of the Earth? Yeah. I don't even need to know the actual mass of this object. The mass of this object shows up on both sides, so that will cancel itself out. So this equation will then turn into little g equals big G times the mass of the Earth over r squared. R here is the radius of the Earth. Why am I using the radius of the Earth? Remember what this r represents? It represents the distance between two objects. Well, if my object is sitting on the surface of the Earth, and we always measure from between the centers of the objects, then that distance between the two objects will be right here. What have I just drawn? I've drawn the Earth's radius, the radius of the Earth. So that's why I can use the radius of the Earth here, the radius of the Earth squared. So I could rearrange this to solve for the mass of the Earth. I would multiply both sides by the radius of the Earth squared. So G, the radius of the Earth squared, equals big G times the mass of the Earth. Divide both sides by big G. I get little g, radius of the Earth squared, over big G. That's going to equal the mass of the Earth. So we could actually calculate this. So we may be tempted to plug things in. Do we remember what little g is? Yeah, little g is on the Earth, 9.8. We have big G right here. And then we could just square this number, right? No, I cannot just square this number. Do you see the problem? Look at the unit of big G. Big G has a meter in it. And what unit is being used to measure the radius of the Earth here? Kilometers. So I need to convert that actually into meters. I'm going to do that real quick over here, just to remind you guys. 6,378 kilometers. In 1 kilometer, the meaning of that prefix kilo is 1,000. There are 1,000 meters. So that's going to equal 6,378,000 meters. I'm going to put that in scientific notation. 6.378 times 10 to the 6th meters. Square that number, multiply it by little g, divide it by the big G, I'm going to be able to calculate the mass of the Earth, which I think is pretty rad that I can do that. So when I do that, I actually get the mass of the Earth equals 5.97 times 10 to the 24, holy cow, this is a huge number, kilograms. And that is indeed the accepted value for the mass of the Earth. So we've just shown that we can find the mass of the Earth. Pretty cool. The big idea here that I need you guys to understand, though, is that the force of gravity, and gravity is an attractive force between any two objects. If I have two objects, they're going to be attracting each other gravitationally. Object 1, object 2. This would be the force of gravity felt by object 1, dealt by object 2. Object 1 is being pulled gravitationally. Object 2 is also being pulled, the force of gravity felt by object 2 dealt by object 1. And that force, those forces are equal to each other, and they equal big G, my proportionality constant, the two masses multiplied together, so the force due to gravity is directly proportional to the mass, and inversely proportional to the square of the distance between them. Let's say that I calculate the force of gravity here, and maybe I get that the force due to gravity felt by 1 dealt by 2, that's of course going to be equal but opposite. Remember, equal but opposite. The force of gravity felt by object 2 dealt by object 1. Let's say that I find that to be a value of 2. What's going to happen? What will the new force be if I double the mass of object 2? What will the new force be? Well, we don't even need to plug numbers in. I just have to do some mathematical reasoning. If I double this number right here in the numerator, what's going to happen to the force? It's also doubled. So the force will also double. Basically, whatever I do to one of these masses, the same thing will happen to the force. If I tripled the mass of object 2, the force will triple. What if I double the mass of object 1, double M1, and triple M2? What's going to happen to the force? The force will increase 6 times, sixfold. It'll be multiplied by a factor of 6. If I double this number, triple this number, that's an increase by a factor of 6. So the force will also increase by a factor of 6. That's pretty simple, I hope. Where I think it gets a little bit more complicated is in trying to figure out what happens if you change the distance between the objects. That's the R value, right? Let's say that I double the distance. Maybe they're 1 meter apart and I've just moved them 2 meters apart. What's going to happen to the force? Well, if I increase this by a factor of 2, 2 squared is 4, that's on the bottom, the force will get cut by a fourth. So the force gets multiplied basically by a factor of 1 over 4. 2 divided by 4 is going to be 0.5. So my new force will be a quarter as much, 0.5. What if I triple the distance between them? Well, if I increase this value by a factor of 3, 3 squared is 9. So the force will get cut by a factor of 9. So the new force is going to be no longer 2, but 2 over 9, which is 0.22 newtons. What happens if I half the distance between them? So think about this. If I cut this in half, if I bring them closer together, we can first of all predict that the force should get bigger or smaller. The force should get larger. If I've cut my denominator in half, if I decrease the number I'm dividing by, then I'm going to get a larger force. So if I cut the radius, or if I cut the distance between them in half, remember this is a square relationship, so if I half R, that's going to be the same thing as multiplying the force by a factor of 4. So if I doubled R, I cut the force by 4, but if I half R, I multiply the force by a factor of 4. I hope you understand that's how this r squared works down here. So my new force should be 8. It's gotten larger just like we predicted. Does this make sense? You guys have got to be able to understand how this equation works and manipulate it mathematically like this. Now, a scientist named Henry Cavendish, who did lots of things in science, he studied chemistry and did some other things, he actually put Newton's law to the test with, I think, a pretty cool experiment. So basically, he suspended from the ceiling, and he did this incredibly carefully in an empty room, no other confounding variables. He suspended from a very, very thin and very flexible fiber, a string. So this thing is capable of rotating. Imagine it's hanging here and it can rotate back and forth. This setup, there's a mirror and there's a firm rod with 2 massive spheres, and it's all balanced. And he brought close to this sphere another massive sphere. Well, remember what the law of gravitation says. If you have 2 objects, they're going to attract each other gravitationally. So if he brings this close, what's going to happen to this whole system? It's going to start twisting. This sphere here is going to be attracted to sphere A, so it's going to want to accelerate this way, which will cause this to accelerate this way. And because the whole thing is stuck on a mirror, the mirror is going to rotate. And if we're shooting a narrow beam of light at that mirror, we can measure the rotation. We can measure how strongly this sphere is attracted. We can measure the rotation of this rod system, because as the mirror turns, the light is going to get bounced off at a different angle. And so that is the scale he created to actually read this. And he basically confirmed that Newton's law was correct, that the closer these objects are, the stronger the attractive force, the more this turns. The more massive these objects are, the stronger the attractive force, the more this thing rotated, and so on and so forth. I think it's pretty cool. So that's Newton's law of universal gravitation.